You ever see a really cool tech demo and wonder, okay, but how do you make that actually work? Make it fast, stable, something you can actually use? Well, that's not magic. It's all about engineering. And today, we're going to peel back the layers on a really cool cloth simulation project to see exactly what it takes to harden a prototype. Let's get into it.
So the whole performance game for this project, it's all built on one core idea: data-oriented design. Now, stick with me here. Normally, you'd group data like, here's a particle, and here are all its properties. But with this approach, you flip that on its head. You group all the positions together, all the velocities together, and so on. It's called a struct of arrays, and it lets the computer just blaze through the data in these super predictable straight lines. It's the secret sauce for everything we're about to see, and trust me, it's a game changer. All right, so we're going to break this down into 4 key challenges. You could almost call them engineering war stories. First up, we're going to fix a beautiful glow effect that was absolutely tanking the performance. Then we'll dig into a jaw-dropping 1100x speed difference between 2 different ways of running the code. After that, we'll get clever and see how you can basically create 3D lighting from scratch. And to wrap it all up, we're going to hunt down that invisible villain of any app that needs to run for a long time, the dreaded memory leak.
Okay, so challenge number 1. It all starts with this beautiful, soft pastel glow on the cloth. It looked amazing, right? But it had a really dirty secret. It was an absolute performance hog. It was bringing the whole application to its knees, making that target of a buttery smooth 60 frames per second just impossible.
And this is the culprit. We're talking over 7,000 individual drawing instructions being sent to the processor for every single frame. I mean, let that sink in. Every single frame. That is just a staggering amount of overhead. So why is that such a bad thing? Well, think about it like this. Imagine you're telling a painter what to do. The slow way is to say, okay, pick up the blue paint, paint one tiny little line. Now put the blue paint down. Okay, now pick up the light blue paint, paint another tiny line, put it down. And you make them do that 7,000 times. The poor painter is going to spend way more time just switching colors than actually painting. That's exactly what was happening inside the computer. The solution? Oh, it's so smart and simple. It's called batching. Instead of that chaotic back and forth, the engineers basically told the painter, hey, just find all the lines that need to be light blue, group them all together into one big shape, and just paint that whole thing in one shot. They created these buckets for each of the 8 main colors and just fired them off one by one. And the result of this simple change? Well, they went from over 7,000 draw calls all the way down to about 24. And no, that is not a typo. It's just a perfect example of how a really smart change in your approach can have absolutely massive results for performance. And this table just lays it all out, right? The new high-quality setting, the one that uses batching, only costs 0.3% of the original. That's a 99.7% reduction in the workload, with basically no visual difference you could even notice. That right there is a huge engineering win. Okay, let's jump to our next challenge. We're shifting gears now from a visual problem to a really fundamental choice about the app's architecture. See, the core physics engine could be run in 2 totally different modes, and the performance gap between them was, well, it was just astronomical. So you've got 2 options here. First is WASM, or WebAssembly. You can think of it as this safe little sandbox. A virtual machine that lets code run anywhere, like right inside your web browser, super portable. The other option is native mode. This is where the code runs directly on the metal, right on your computer's hardware. No middleman, just pure maximum speed. And wow, this chart just says it all, doesn't it? To update just 1 frame of the simulation, the WASM mode took over 135 milliseconds. And the native code, 0.122 milliseconds. Look at those bars. That's not just a small difference. That is an absolute chasm. To put a single number on that gap, the native code was roughly 1,100 times faster. 1,100. Let that sink in for a second. This isn't a 2x or a 10x improvement. We're talking over 1,000 times faster. So what's going on here? Why was it so much slower? Well, a few reasons. The WASM setup was basically interpreting the code on the fly, translating every single instruction as it ran. It couldn't take advantage of special ultra-fast hardware pathways called SIMD, and all its safety features, which are great for security, added extra checks and overhead to everything. So all that portability and safety, it came at a really, really steep price in terms of speed. And here's what that actually means for you, the user. For a smooth 60 frames per second animation, you've got a time budget of about 16 milliseconds to get everything done for that frame. The WASM version needed 812% of that budget. I mean, it's just not even close. The native version, on the other hand, barely made a dent, using less than 1% of the budget. Total night and day.
All right, challenge number 3. This one is cool. We're going to shift away from raw performance and into the realm of pure algorithmic creativity. The simulation itself is actually just 2D. It's a flat grid of points. So the big question is, how do you make a flat thing look and feel like a three-dimensional shaded piece of cloth?
Yeah, this was the central puzzle they had to solve. Without some big, heavy 3D graphics engine doing all the work for them, the engineers had to get clever. They had to invent a way to calculate realistic lighting and shading for every single one of those tiny triangles making up the cloth.
And the solution is just this beautiful, elegant, 3-step fake. It's awesome. First, they figured out a virtual depth for each point. Basically, if the cloth is all bunched up, that part is closer to you. Okay, step 2. Using that fake depth, they could calculate which direction each little triangle was facing in this made-up 3D space. And finally, they just applied a standard lighting formula to shade the triangle based on its angle to an imaginary light source. So clever.
The specific recipe they used is a classic trick called Lambertian diffuse lighting. It's just perfect for faking how light hits a matte, non-shiny surface, like cloth. The basic rule is simple. The more a surface is facing directly towards the light, the brighter it gets. And that simple rule is what creates all those soft, believable shadows you see in the folds. You know the best part about this whole illusion? It's dirt cheap to compute. We're talking about 30 simple math operations per triangle. For a modern computer, that's nothing. It's a drop in the bucket. It's just a perfect example of how a super smart algorithm can give you this massive visual impact for a tiny, tiny performance cost.
Okay, on to our final challenge. And for this one, we're hunting an invisible enemy. Look, an app can be super fast and look amazing, but if it's slowly eating up all your computer's memory over time, what we call a memory leak, it's eventually going to slow down, get unstable, and crash. Preventing this is a non-negotiable part of hardening a prototype.
The team knew exactly where to look. Certain parts of the code were like potential leaky faucets. Anytime the user interface code had to talk to the core physics engine, or whenever new graphics objects were being created, there was a risk that memory would be used but not properly cleaned up later. These were the spots they had to watch like a hawk.
And to fight this, they didn't just cross their fingers and hope for the best. No, they turned it into a science. They created this super strict memory budget. For instance, after the app had been running for an hour, its memory usage was not allowed to grow by more than 2 megabytes. Simple as that. This took the vague fear of leaks and turned it into a concrete, measurable engineering goal. And, this whole thing was really a tag team effort between 2 different programming languages. On one hand, you had Swift, which handled the app's user interface and all the high-level stuff. But for the high-performance physics core, the part where every single nanosecond counted, that was written in Zig. It's a language that is just perfectly built for that data-oriented design we talked about way back at the beginning. So, from squashing graphical bottlenecks to faking 3D light and hunting down invisible memory leaks, we've really seen the kind of deep engineering craft that's required to make software truly solid. And it really makes you think, doesn't it? The next time you're using an app on your phone or computer and it just feels fast and smooth and reliable, take a second to think about the invisible work that went into it, the clever algorithms, the disciplined testing. What unseen engineering craft is powering the apps you use every single day?